Well, hello everybody. It's Dave here today to begin our unit on fluids in the AP curriculum. We're going to split this up into two sub-concepts. The first will be hydrostatics, where the fluid's not moving, followed by hydrodynamics, where we will now move the fluid through a system. The typical first question that we like to ask is a question that looks like this. There are four different vessels of different shapes, and we see that there is this height at which all the vessels are filled, and there's a red line at the bottom, and the question is, which of these has the greatest pressure at the red line? Hopefully by the end of this lesson, you'll be able to answer that question. It is important to have an understanding of the different states of matter before we continue. Hopefully you've learned this at some point in your education, but there are three primary states of matter that we typically look at: solids, liquids, and gases. Plasma is typically listed as the fourth state of matter. You'll notice, though, in the definitions that there's an important element that I want you to recognize. When we're defining a solid, it has a definite shape and volume, whereas with liquids and gases, they take the shape of their container, and of course, in the case of gas, it also takes the volume. There are other states of matter to look at as you move through your education in physics. A Bose-Einstein condensate is an interesting one to talk about, to say the least. So we have to define these materials by some quantity, and that is almost always going to be its density. You've probably heard the question, what's heavier, a ton of feathers or a ton of bricks? And the answer is they're the same. However, if we talk about it in terms of density, the ton of feathers would take up a far larger volume over the ton of bricks. And so when we talk about density, then, we're going to use the Greek letter rho to define this as the mass per unit volume, where in SI units, they are kilograms per meter cubed. There is one quantity that comes up a lot in your unit of fluids, and it's this idea of the specific gravity. And that's just taking the density of your substance and taking its ratio with respect to the density of water. So we need to understand what our definition of a fluid is. The constant misconception is that a fluid is in fact a liquid, and that's not necessarily true. A fluid is a material that is unable to withstand a static shear stress. So what does that mean? It means that it's easily manipulated. If you think of something like a solid, if we put some force on it, there is this shear stress that it can actually withstand and therefore deform. When it comes to a liquid or a gas, that's not necessarily true. They can actually be manipulated and moved according to wherever the forces are being applied. What that means is then, when we're speaking of this unit of fluids, we have to include both gases and liquids in this discussion. So where is the usefulness of this concept of fluids? Well, the neat part about it is for you is that there are so many applications by which fluids play an essential role in things like airplanes flying and things like hydraulics. These basic concepts are actually the governing principles behind what's going on. If we talk about liquids specifically, for example, we always consider them to be incompressible. The idea being that if you push down with a piston on a liquid, it won't actually compress. In reality, there is absolutely cases where we can compress a liquid, but it takes an immense amount of force to do so. So for the sake of this course and this content, we are going to consider the liquids to be incompressible. Well, given that nature, that means that if we do work on the fluid from one end, then it has to perform some sort of pressure on the other end based upon this incompressibility. So there's definitely going to be some relationships that will be very useful moving forward. So let us define pressure as the force per unit area, where the units of pressure are given in newtons per meter squared. You may also see them in kilograms per meter second squared if you substitute in for newtons as kilogram meter per second squared. So let's do a quick example problem that involves these concepts. Let's say we have a waterbed that is 2 meters on a side and 30 centimeters deep. And our first question is finding its weight if the density of water is 1,000 kilograms per meter cubed. Well, we know that the volume of any rectangular prism is length times width times height. So we can simply plug those values in to give us an answer of 1.2 meters cubed. From there, we can use our density equation to find the mass of water in this waterbed. And so we know that the density of water is 1,000 kilograms per meter cubed. We know that the volume of water is 1.2 meters cubed. So when we multiply those together, we should get 1,200 kilograms. That gives us a weight of this waterbed at an alarming 11,760 newtons. Quite heavy. For part B now, let's say we have to find the pressure that the waterbed exerts on the floor. Assume that the entire lower surface of the bed makes contact with the floor. This is an important element because, again, if we're talking about pressure being force per unit area, if we didn't have the full surface area of this rectangular prism on the ground, then it would actually localize the force more and it would increase the pressure. So in this case, pressure is force per unit area. We know that the force is simply going to be the weight of the waterbed itself, and we know that the surface area associated with this is 2 times 2, or 4 meters squared. Again, this is assuming that the waterbed itself doesn't change shape, and that gives us a pressure of 2,940 newtons per meter squared. So hopefully these are fairly straightforward problems. So let's imagine now that we have a vessel with a fluid in it, such as a liquid, and it's at rest. Because it's at rest and there's no velocity or flow associated with it, we consider this to be a discussion of hydrostatic pressure. And when we submerge objects, in this case we're submerging a cork and a lump of aluminum and a lump of lead, there are two things that will happen when you submerge these objects. The first thing is that a fluid will exert a pressure in all directions. Okay, so that means the object, that also means the vessel walls itself. And the additional thing to remember here is that when a fluid exerts this pressure, it's always going to be perpendicular to the surface that it interacts with. So when you take a look at the picture here of the three objects submerged in this fluid, you'll notice that we have vector arrows all pointing in towards the object, but you'll also notice that the length of those arrows are different. And that's because, as we know from vector understanding, the length of the vector should represent the magnitude, meaning that the amount of force that these objects are experiencing at a lower level is actually higher than the force above. We're going to get into what that means when it comes to the quantitative end of this shortly. But the important thing to recognize here is that the force vectors are all around it, and depending upon the depth of those arrows, you'll notice that the length of the arrow is changing, indicating that the magnitude of the force is changing as well. All right, let's take a look at an example like this. We have an object, which in this case is a cylinder, and it is put in the water so that it just sits at the surface, but the entire volume of the object is submerged underwater. Well, if we have to draw a free body diagram to describe all the forces at play, there are actually three that are present. The first, as always with any massive object in a gravitational field, there is the weight of the object pointing down. There's also this force associated with the fluid that is the atmosphere pushing down on the top of the object. Remember that this object is submerged fully, but the surface can be interacted with this atmosphere above it. And then there's an additional force of the water actually pushing up on this object. Now, we are going to consider the case where this object is stationary so that it's not accelerating up or down. And in that particular case, the net force equation would have to be that the force caused by the water is equivalent to the force of the atmosphere plus the weight of the object itself. Well, we can get into the fluid discussion of this a little more now if we speak of this in terms of pressure. And so if we take a look at the pressure equation, we see that pressure is equal to force per unit area. Well, we had a net force equation. Let's go ahead and solve that equation for force, which in this case would be pressure times area, and we'll substitute in for our expressions of force. You'll notice that for the force by the atmosphere, I've labeled that as P naught. That could mean the initial pressure of anything, but in this case, it's going to mean the atmospheric pressure. Well, there's another definition that we also know, and it's this definition of density. And again, as I have stated before, you're going to find that we want to refer to objects in terms of its density and volume as opposed to just its scalar quantity of mass. And so if we actually solve this equation for mass, we get that mass is equal to rho times v, where rho is the density of the object and v is the volume of the object. And if we substitute this in now for mass in the expression of its weight, we get the equation that you see before you. So if we take a closer look at this equation, we can see that P represents the absolute pressure, P naught represents the initial pressure, which may or may not be the atmospheric pressure depending upon the question, and then rho GH in our example was actually the weight of the object. You will find that in general when we use this equation, H will be the depth below the surface. There's another quantity that's worth discussing, and it's this idea of gauge pressure. And gauge pressure is simply P minus P naught, or stated differently, delta P. And it's important to recognize this notation because if we are asked for the gauge pressure alone, we only calculate with rho GH. If we're asked for the absolute pressure, we have to include rho GH with P naught. Again, the way I think of gauge pressure is what the gauge would read to represent the pressure associated with our given scenario. Let's do an example problem to see this equation in action. Let's calculate the absolute pressure at an ocean depth of 1,000 meters. Let's assume that the density of water is 1,000 kilograms per meter cubed and that the initial pressure is 1.01 times 10 to the 5 pascals, or in another unit, 1 atmosphere. Well, we know that our hydrostatic pressure is P is equal to P naught plus rho GH. We have all our quantities, so we can quickly substitute those in to get an answer of 9.9 times 10 to the 6 newtons per meter squared. The trickier question comes when we have to do something like calculate the total force exerted on the outside of a 30 centimeter diameter circular submarine window at this depth. Well, in this case now, we know the exterior pressure is 9.9 times 10 to the 6 newtons per meter squared. We know that it is going to be interacting with the area of the circular window itself, which we can calculate with pi r squared. And so with our equation for pressure, we can simply solve for force to get our answer of 7 times 10 to the 5 newtons, a significant force for sure. There's an important application that we can apply to this when we close the system and put a liquid inside. We know that a liquid is considered to be incompressible, which means if we apply some pressure to one end of the system, that pressure should transmit all the way through the liquid and actually end up as the same pressure on the other side, or P1 equal to P2. Now, that's an interesting statement because even though the pressure has to be the same, the force doesn't necessarily have to be the same if the surface area that it is applied to is changing. And so this is an idea that we know as Pascal's principle. And by definition, Pascal's principle is that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So again, this is taking advantage of the fact that we are considering liquid to be incompressible. So take a look at the example that we have here. This is a classic mechanics lift, and you'll see that in the bottom left diagram, we are going to apply some force to this cylinder, which has a cross-sectional area of A1. And we are going to displace it down a distance that we'll just call delta x. Well, because of the incompressible nature of this fluid, what happens is there is now a lifting force on the other side where it is a larger area, and that means that because of the larger area, we're going to end up with a smaller vertical displacement. So if we take a look at this mathematically, we can see that on the left-hand side, we've applied a force F1 over some cross-sectional area A1, and that change in pressure is actually going to be the pressure that transmits through this fluid until it gets to the other side and applies the same pressure to the bigger cylinder. And so we have this equation where the pressures are equal to each other, but we know that the areas are not. We do, however, know that the actual volume displaced on the left has to be equivalent to the volume on the right, which means we can take our definition of volume as being the cross-sectional area times the displacement vertically to simplify our equation to F1 d1 is equal to F2 d2. This hopefully rings a bell because this is in actual fact the equation for work. And so a different way to define the application of hydraulics is that the work being done by a small moving piston has to be equal to the work being done by a large piston when it is trying to raise a truck. It is an exceptional application. Another application involves the idea of creating pressure gauges. And so this contraption right here is known as an open tube manometer or a manometer. And if we have some unknown pressure on the left, which we'll call P, And we know that there is some initial pressure on the outside, the atmospheric pressure, which we'll label as P naught. Then the pressure at B should be what we've already understood from our hydrostatic pressure as P naught plus rho GH. But by definition, because we know the pressure at B is at the same height as the pressure at A, then we should also know that the pressure at A, which is P, should be equivalent to the pressure at B, which is P naught plus rho GH. So again, we have another application of hydrostatic pressure where we end up with this known equation. As a reminder, the gauge pressure is P minus P naught. So if we actually had some sort of mechanical gauge to read the pressure there, that would be the pressure that it reads. An extension to this application is a barometer. And the construction of a barometer looks like this. We have a tube that is filled with mercury and then placed inverted into a vessel that also has mercury. Some of the fluid will flow into the vessel until it reaches equilibrium. Well, at the top of this now closed end of the tube, there is no air in existence, which means there's actually no pressure because it's a vacuum. The external pressure, which is causing it to maintain this equilibrium, well, that's just the atmospheric pressure. And due to the height above the surface, we can actually use our hydrostatic equation to calculate what the external pressure is. This is how a barometer works. Now, back in the day, they used to refer to the units of a barometer in terms of millimeters of mercury. We've come a long way since then, and now we refer to pressure in terms of either pascals or in terms of atmospheres. And an atmosphere, by definition, is just the equivalent of a column of mercury that is exactly 0.76 meters in height at 0 degrees Celsius. Let's shift now into a different concept. Everybody here has hopefully been in a boat before or floated on the water or submerged themselves underwater and noticed that you typically will pop up. Well, the reason for that is because there is this upward force caused by this immersion in the fluid known as the buoyant force. Now, we take a look at a couple of different examples here. We see in the left-hand example that there is this object floating on the water, and the reason for that is because when it submerges into the water, it's not fully underwater, but it displaces fluid. And because it displaces fluid, the result is this buoyant force which pushes up against it. In the case of the right two examples, you can see that if we initially have just a volume of water and we put an object in there, that object should be displacing an equivalent volume of water, and it is this displacement of volume that causes the buoyant force to be felt. And so by definition, Archimedes' principle states that an object is buoyed up by a force equal to the weight of the fluid displaced. And so if we take a look at the diagram here, we see that an object hanging from a Newton scale reads 7 pounds. And if you put it underwater, it actually reads at 4 pounds. And that's because there is this buoyant force which is lifting it up with a force counteracting the weight by 3 pounds. You can see in addition that if we take a look at the water that was displaced through that tube at the top, that would be equivalent to 3 pounds of water. So this is Archimedes' principle, and this is the important thing to recognize, is it's equivalent to the weight of the fluid displaced. Now, we can define some equations to help us out with buoyant force. We know that we're talking about the weight of the fluid. But as I said before, we don't deal with mass in terms of mass anymore. We deal with it in terms of density times the volume displaced. And so when we substitute that in, we get this equation of rho Vg. And in this case, the volume of the object is equivalent to the volume of the fluid. So if we know the density of the fluid and we know the volume displaced because we know something about the object, we should be able to determine the buoyant force associated. Let's do the classic buoyancy problem. There is a historical story behind this in which King Hero hired a goldsmith to create a crown for him. And when he did so, the goldsmith ran off, took this lump of gold, created a crown, and then came back and showed his masterpiece. King Hero was not a very trusting individual, and he thought that the goldsmith had actually stolen some of the gold. So he hired Archimedes to determine whether the crown itself was pure gold or if it was a mixture of gold and some other materials. What Archimedes did is something very similar to this problem that you see before you. We take the crown and we weigh it in the air. In this example, it's 7.84 newtons. Then you weigh the crown when it is immersed in water, and you get another scale reading, which in this case is 6.86. We know that the difference between the forces is because of the buoyant force. And so if we take the force that we measured in the air and we subtract the force of the object when it was in the water, we should get the buoyant force, which in this case is 0.98 newtons. We can use then our equation for buoyant force as rho Vg. We know the density of the fluid, it's 1,000 kilograms per meter cubed, and we know what G is, so we can actually find the volume of fluid to be 0.0001 meters cubed. Well, we know by definition that that has to be equivalent to the volume of the object itself, so we now know the volume of the object, and using a simple equation for gravitational force is equal to mg, we can find the mass of the object to be 0.8 kilograms. That gives us a calculated density of 8,000 kilograms per meter cubed. If this in fact were pure gold, then that density should have been 19,300 kilograms per meter cubed, and this gave the evidence to Archimedes to go to King Hero and say, aha, your goldsmith took an early retirement fee, and from there, I'm sure we know what history would do to that goldsmith. So, classic example involving buoyant force, dealing with net force equations, applying that to density, applying that to our buoyant force equation to begin with. So there is one idea that we haven't talked about yet, and it's the idea that some objects actually naturally want to float, and some objects naturally want to sink. And the question is, how can we tell the difference? Well, it comes down to this discussion of density once again. So let's take an example first where the two objects are actually submerged fully in the fluid. If we talk about the net force equation on those objects, we know that there's a buoyant force pointing up and there's a weight that pulls down. In the case of the object on the left, if we calculate the net force, we know that that's rho gv in terms of the fluid minus rho gv in terms of the object. Well, an interesting discussion happens now depending upon the density of the object itself. Because if the density of the object is less than the density of the fluid, then the resulting force will be positive pointing up. On the other hand, if the density of the object is greater than the density of the fluid, our net force will actually be a negative net force, which means that in this case, the weight of the object is overcoming the buoyant force pointing up, and the acceleration of the object will be down, and so it sinks. So knowing something about the fluid and the density of the object should tell us whether an object is going to float or sink. But what about the case now when the object is actually floating in the water? Well, we know that if it's floating, that it's not accelerating up or down, which means that the net force on the object is equal to 0. If we apply our equation for force given density and volume, we know that rho gv of the fluid should be equal to rho gv of the object. Now this is where it gets a little tricky, because when we're talking about the volume of the fluid, it's not going to be the full volume of the object. It's actually going to be whatever amount of the object is actually below the surface. If half of the object is below the surface, that means that half of the object's volume is the volume of fluid that was displaced. And so if we take a look at this equation, we can see that we can actually get rid of G altogether, and we can simplify this into a ratio of volumes being equivalent to a ratio of densities. This is a highly useful equation because now, if you understand the nature of the fluid and the nature of the object, you can begin to determine things like how much of the volume will be displaced by the object, how far down will the object sink. So, we've taken a look at this idea of hydrostatic pressure, and then we applied it to this idea of buoyancy and this idea of a buoyant force. Good luck with your practice problems, everybody. We'll see you next time.